Hello everyone, welcome to this course on CFD modeling using ANSYS CFX. Now we will see a CFX case study, which is a sample simulation which we have conducted using CFX. We will see different case setup, how to define the problem, how to solve the problem, how to extract results of this particular problem and analyze the results and make sense of them. This particular problem is on flow through a duct bend, and we are going to see the effect of guide vanes in this particular duct. We are going to consider a case of high turbulent flow without guide vanes to start with. So the first simulation will be high turbulence flow without any guide vanes, and after that we will see the effect of guide vanes also. So consider a duct bend as shown in the figure. This is a sort of a L-shaped duct bend. The cross section is a rectangular. We will be walking through the entire analysis of this problem, which is a flow through a duct bend. The mesh is already generated, so we won't be seeing any process of mesh generation. Mesh, as usual, we generate with ICM CFD. We will import the mesh into CFX pre in this particular case study. We will set up the physics. We will run the solver from CFX solver manager and then view the results in CFD post. After completing the simulation, we will add two guide vanes. We will turn on the heat transfer model and we will run it again and see the results also in this case study. So what are the different problem definitions of this problem of a flow through a duct bend? Operating conditions is that the fluid is air at 25 degrees centigrade. Inlet speed is 10 feet per second, which corresponds to a Reynolds number of 9 into 10 to the power 5, and which is high turbulence regime. The outlet is opening with flow direction being normal and relative pressure of 0 pascals. If there is any backflow, the turbulent intensity for that is 2.5%. To set up this model, we will do following things. We will import the mesh, we will define the computational domain, then we will set the boundary condition, we will set the inlet boundary condition, the outlet boundary condition, symmetry planes on the side surfaces because we are using a symmetry concept. Then we will set the initial conditions and define the solver parameters. First, start CFX. How do we start it? First thing that we do before starting any CFX problem is make a folder in the D or E drive with your name and set this as the working directory. Then we start CFX pre from either the ANSYS CFX launcher or command prompt. After that, we start a new simulation within CFX. We select the general mode option, save the simulation as duct bend. So this is how the name will appear, duct bend. After that, we import the mesh file, which is named as ductbendmesh.gtm. We expand the tree and see the 2D and 3D regions which are part of this duct bend geometry. There are two 3D regions. Then we go to the domains, that is the 3D domains that are part of the simulation. We double click on default domain. We do not change the basic settings. We understand just the location, material, etc. Then we click on fluid model and turn off the heat transfer equation. So what we do is, in the equations section, in the heat transfer, we select as none. We click on OK in the panel. Next is boundary conditions. We create the inlet boundary condition. We set the boundary type as location. For creating inlet boundary condition, we click on this icon. Inlet boundary condition, the boundary condition panel pops up. In the basic settings, we input as inlet. We set the boundary type and location. In location, we select the in as the geometry part or geometry surface. We set the inlet normal speed of 10 feet per second. Then we create an opening boundary with a relative pressure of 0 pascals, and here we select the type as outlet and the location will be the outlet surface. We select the backflow intensity as 2.5%, which is a fraction of 0.025. Then the third boundary condition that we have to set is the symmetry boundary condition. We define the separate symmetry boundary condition on symmetry 1 and symmetry 2. These are the surfaces that are part of the simulation geometry. The boundary, after we set the symmetry settings, the boundary default domain default is created automatically. All remaining external surfaces will have this default boundary condition of no slips, that is smooth walls. So we don't have to do any separate settings for walls. We have not created any internal boundary condition, so the flow will not see any veins and pass straight through them irrespective of whether the geometry of veins is present or not. So this is the boundary condition that are applied. This is the inlet, this is the outlet, and this is the flow boundary condition, whereas this is the symmetry surface. After that, we initialize this problem. Initial values for all solved variables must be set. Initialization option is obtained by clicking this icon. There are two options. The automatic option will use existing solution variables if they exist, otherwise the solver will generate an initial guess, and automatic with value option. For versions lower than 12.0, check the turbulent eddy dissipation box also. Leave all the options set to automatic for this case. As a first guess, the solver will make some simple intelligent assumptions to get things moving. Too many details to discuss here, but we can write a backup file before the first iteration to see the initial guess. Then there is the solver control, which is obtained by clicking this particular icon. Define the solver control options. The advection scheme is defined as high resolution. The convergence control, we set auto time scaling. Maximum number of iterations are defined as 100. Length scale option is conservative. Then the convergence criteria is set as 1e to the power minus 4. Then we start the solver. Click on define run icon to start the solver. This will write the .def file. We save it as duct_bend. Now let us see how to progress in CFX solver. We start the run in CFX solver. Once the residual plots appear, switch between RMS and maximum. We create a new monitor plot and monitor the imbalance also. So these are the mass imbalance, the momentum imbalances that we plot. Create another monitor plot and monitor flow outlet, that is mass flow at outlet. When the CFX run is finished, we have to view the results in CFD post. Now going to CFD post, we have to go to object selector, list currently defined graphic object, that is boundary created automatically. We can create, edit, duplicate and delete objects as well. We have to use icons on the right. So we have to right click here and go on creating new objects. We can toggle the visibility. Object editor is there where we can edit the properties. We have seen all this in the CFD post lecture. So go on creating your own planes, locators and view contours and vectors on them. So an example is shown here, which is a plane 1 and definition is an XY plane at Z equal to 0.05 meters. We have colored the plane by variable pressure. This plot will be used to compare in the next case where there will be guide vane. So we'll compare this pressure without guide vane with pressure field with guide vane. We will also plot vectors which can be plotted on the same plane. We insert a line. Under definition, we create 2 points. For creating line from a point which is defined by 0.7, 0.1 and 0.05 as the coordinates to a point which is defined by 0.7, 0.4 and 0.05 as the coordinates, we click on apply. Now on this line we will plot the variation. So we insert chart. Under data we click new. Under location we select line 1. Under x-axis data selection we select the variable as velocity, and under y-axis we select the variable as y. So what we are going to do is we are going to plot velocity as a function of y coordinate on this particular line. We click on apply. We have seen only 2 entities, but you can try out other features like contour plots, streamline plots, and save the CFX post state so that definitions like line chart can be used for further studies. Now let us shift to a case with guide vanes, and we are also going to turn on heat transfer. The same case will now rerun with the heat transfer on and 2 turning vanes. To do this, we need to modify the domain settings and add boundary conditions for the vanes. Since the heat transfer model requires more information at some of the boundaries, changing the model will cause inconsistencies in the definition of these boundary conditions. These will appear in red in the object selector with a corresponding explanation in the physics error summary. We can correct this automatically by right clicking on the red text and selecting autofix physics thus taking the defaults. In other cases, a value may be required. Duct bin with vanes, what is the problem definition? It remains almost same. Area is 25, we are going to consider fluid with air at 25 degrees centigrade. Inlet normal speed is 0.1 meter per second. Inlet temperature is 300 Kelvin and outlet static pressure is 0 pascals. To modify this model, we will need to modify the domain models, modify the inlet boundary condition, create boundary conditions for the vanes, and modify the initial conditions. If you have edited CFX, if you have exited CFX pre, launch CFX pre and open the existing simulation file, edit the existing domain, that is default domain, change the heat transfer model to thermal energy, which is shown here, and click OK. Now we have to edit the boundary conditions. For this, the inlet boundary condition appears in the red in the object selector. It requires heat transfer information. Edit the inlet boundary, set the temperature to 300 Kelvin. The outlet boundary appears in the red in the object selector as well. It requires heat transfer information. Edit the outlet boundary and enter the opening temperature to 300 Kelvin again. We have to introduce vanes as thin walls. For that, we create a boundary condition for the first turning vane, that is vane 1. The boundary type is selected as wall. Location is vane 1. Heat transfer temperature we have to set to 350 Kelvin. For vane 2 also we use the same setting. There is no slip wall and temperature is 350 Kelvin. Next we write the solver output file by pressing on the right solver output file icon. It will save a .def results input solver input file. We do not start the run yet in solver manager. While the solver is running, we will change the timescale settings from auto timescale to physical timescale and specify the physical timescale. Looking back in the output file for the first case, the auto timescale is reported to be 3.57 e to the power minus 2 seconds. Since the auto timescale is usually somewhat conservative, we will replace it with a physical timescale of 3.5 into e to the power minus 1. This will increase the speed of the simulation. We can get quicker results. So for updating the timescale, start the run and let it run for 10 iterations. Open the CFX command language editor for the run in the progress. Expand the command language CFX command, expand the CCL tree to view the convergence control, which is located here, and change the timescale to physical timescale by double clicking on it. Delete the length scale option parameter by selecting it and then using edit delete parameter. Add a physical timescale parameter by clicking on convergence option and selecting edit, add parameter, enter the value 3.5 e to the power minus 1. Click OK. Save and exit from the CCL editor. When you update a parameter, a few things happen. Solver writes a backup file. Changes to the CCL are shown in the output file. Run continues after that. Once we have got a converge result, we have to open CFD post. When prompted on the solver manager, start CFD post and shut down CFX solver. Load the previous CFX file state by importing file duct_bend.cst so we can compare both the results. The objects and plots that were previously created are now updated to the new results. Examine the existing results to see the effects of the turning vanes in CFD post on the flow. A comparative study can be performed by loading previous result file. For that, go to File, Load Results. Under Case option, activate Keep Current Cases Loaded so we can load both the cases at a time. Choose the previous result file without vanes or heat transfer and then click Open. This is the comparison. The left image shows guide vanes. The right image does not show any guide vanes. We can see that the wake region or the low pressure region after the bend is reduced when we use guide vanes. The flow is much more distributed now. So here is the pressure comparison. The low pressure region without guide vane is now reduced. Separation region is reduced by using the guide vanes. The flow is more directed. Also, the high pressure region near the bend is reduced, which gives a sort of a good stability to the entire structure. Due to high turbulence, there is no recirculation region in either case. the velocity profile is more uniform nevertheless in the case of guided vanes. So comparison of the two velocity profile is shown here. Although there is not much recirculation, we can see that the velocity profile is more uniform in the guided vane case, which is actually the blue one. So thank you for listening to this particular case study on high turbulent flow through a duct bend with and without guide vanes. See you in the next session of the CFX course by LearnCAx.